Good afternoon, everyone, and welcome to the session number 5 from the chapter of magnetism and matter. The topic is the derivation of the equation for the magnetic field on the equatorial line of a bar magnet. So, this is a bar magnet, and this is the south pole of it, and this is the north pole. And the equatorial line is the line which is perpendicular to the magnetic axis of this bar magnet and passes through the geometric center. So the O is the geometric center of this bar magnet, and this is the point P, which is lying on the equatorial line, and this point P is at a distance of R from the geometric center. So here the magnetic field due to the north pole, which here is depicted here as Bn, will be directed from N to P, and its magnitude will be equal to mu naught upon 4 pi into M, where M is the pole strength, divided by the distance of this point from the north pole whole square. So the distance of this point from the north pole is equal to under root R square plus L square, where 2L, this 2L is the magnetic length of this bar magnet. So ON will be equal to L, and this is also equal to OS. So this is L, this is R, so NP will be equal to under root R square plus L square. So the magnetic field due to the north pole at this point P will be directed from N to P, and its value will be equal to mu naught upon 4 pi into M. M is the pole strength divided by the distance ka whole square. So this is equal to under root R square plus L square whole square. Similarly, the magnetic field due to the south pole will be equal to mu naught upon 4 pi into M divided by under root R square plus L square ka whole square, and the magnetic field due to the south pole will be directed from P to S as indicated by this arrow. So here one more thing, that this mu naught is the permeability of the free space. So here in this case, as we can see here, that the vertical component of the magnetic field due to the north pole and the south pole will get cancelled out, because the magnitude of the magnetic field due to the north pole and the south pole are equal. So the vertical component will get cancelled out, and the net magnetic field will be due to the horizontal component of Bn and Bs, and the horizontal component of both these two magnetic field will be directed in this direction. So the direction of the net magnetic field will be from the north pole towards the south pole, and its magnitude will be equal to mu naught upon 4 pi into M divided by R square plus L square, because the square of the under will give us R square plus L square into cos theta. Now cos theta will be equal to, here cos theta will be equal to L divided by under root of R square plus L square. Here cos theta will be equal to L divided by under root R square plus L square. So the horizontal component, because of this magnetic field due to the north pole, will be equal to mu naught upon 4 pi into M divided by R square plus L square into cos theta, plus the horizontal component and this horizontal component of the magnetic field due to this south pole will also be the same, that is mu naught upon 4 pi into M divided by R square plus L square into cos theta. Now if I add both these two, I will be getting this value, that is mu naught upon 4, here cos theta will be equal to L upon under root R square plus L square. So by substituting the value of cos theta here, I will be finally getting this value, because cos theta will be equal to L divided by under root R square plus L square. So in the this denominator, I will be getting R square plus L square to the power 3 by 2, and in the numerator I will be getting mu naught into 2 into M into L and in the denominator I will be getting this, this is 4 pi into r square plus l square to the power 3 by 2. Now 2 ml is the magnetic moment of this bar magnet, and so I have substituted this 2 ml by capital M. So finally I am getting the net magnetic field on the equatorial line of this bar magnet, which is equal to mu naught upon 4 pi into capital M divided by r square plus l square to the power 3 by 2. Now if the bar magnet is very short, if for a short bar magnet, this L is very less in comparison to R, so this can be neglected. So if L is neglected, then I will be getting the magnetic field for a short bar magnet, which is equal to mu naught upon 4 pi into M upon R cube, and this magnetic field will be, the direction of this magnetic field will be from north pole towards the south pole, and it will be opposite to the direction of the this magnetic dipole moment. The direction of the magnetic dipole moment is from the south pole to the north pole, but in this case the direction of the magnetic field is from north pole to the south pole. So the direction of the magnetic field is opposite to the direction of the magnetic dipole moment. So thank you very much for joining this session. In the next session now I will be coming up with a couple of questions from the topic of this magnetic field on the equatorial line of the bar magnet, and on this magnetic field on the axial line of the bar magnet. So I will be coming up with a couple of questions in the subsequent 2 or 3 sessions based on these two topics. So till then, have a nice day. Bye.